the last segment, we introduced the idea of the joint distribution, the marginal, and the conditional probability models, and we developed the marginal and the conditional from the joint. However, it's usually the case that it's a lot easier to develop the marginal and the conditional models than it is to obtain directly what the joint model would look like. So one of the uses of that previous work that we talked about is just that, to obtain the joint from the marginal and the conditional. We're going to use that basic concept of what these different distributions mean in their relationships to do that, and we're going to return to the traffic counter as an example. So in general here, that relationship between the joint and the marginal conditional is that we can look at the joint as being the conditional mass function for x and y, and since we conditioned on y, then we want to multiply by the marginal of y. Or it might be the other way around, that we want to instead, or have prior information about y given x, and so then we'll multiply by the conditioning event likelihood. And indeed, it's really this last form here that we have that we'll use later on in the Bayesian approach of how to update the likelihoods of accuracy of our instrument. Okay, so let's go back, and instead of having that empirically based model for the traffic control, instead we might want to come up with an analytical model for the joint distribution for that traffic counter rather than traffic control. And note that our vehicles were really Poisson arrivals. Right? Think back to all of the dimensions and aspects of or assumptions of the Poisson of having actually Bernoulli trials, that there is a constant rate, right? And we're going to do the flip-floppy on you here. Instead of using the parameter lambda, we're going to use the parameter nu. Remember that Poisson model was the arrival, the number of vehicles, right, was equal to this parameter raised to the x power times e to the minus nu power over x factorial. And x could take on values of 0, 1, 2, so on and so forth, up to infinity. Now, in practice, what we saw in that last numerical example is that x didn't take on any values greater than 4 from that one restricted observation of 400 intervals, yes, but still that's just a subset of the overall possible. And so theoretically you could have an infinite number of vehicles, and we're trying to create a model that's a little bit broader than that, right? And remember from the Poisson that our expected value, or our average here, was equal to nu. Average number of arrivals in our interval. In our case, a 30-second interval. If we wanted to do this on a minute or 2 minutes or something like that, we can reinterpret the data to get a new, pardon the pun, a new for that parameter, right? So from before, in our sample, we had that our x bar, right, that's our sample mean, and if we go back to that what we had before. We had observed values of 0, 1, 2, 3, and 4, and we had these proportions. Here's our marginals values that we came out for each one of those x's. Right, so keep that in mind as we write down the following for our average. We had 0 vehicles show up 100 out of 400 times. We had 1 vehicle show up 160 out of those 400. We had 2 show up 80 out of the 400 times. We had 3 show up 40 out of the 400 times. And we had 4 show up 20 of the 400 times. And work that out, and that is equal to 1.3. So we're going to learn in our next segment about point estimates or parameter estimation. For right now, without any significant discussion about it, we're just going to set our model parameter equal to what we observed in the specific sample that we took. Okay. Also from before, we know that the probability of error that each car is recorded with probability of about 0.9. It was 0.8725, but for simplicity here we're going to round that up to 0.9. Right? And so that should make us start thinking a little bit about some of these other models that we've developed in previous lessons, right? That given x is equal to some specific value, call it xi, right? So we have a certain number of cars that are arriving in a specific interval. We have, in some sense, x trials, each with success of recording them of little p, right, of 0.9. And so that should make you think about that table that we had, KP 6-1, and we're looking at how many successes or arrivals in a fixed time interval. That's the binomial model, right, with n as our number of trials and p as our likelihood of success. Right? Notice here's our Poisson model, and that's why I used the new symbol instead of lambda, and I know it gets very confusing because we got nu equals lambda t here, but in your text the role of lambda and nu are switched. I chose to use nu here because of this table being in your hands, and therefore wanted to be consistent with that particular table. Right, so here's this binomial model that we're after here that is really our conditional model, right? That given that x is equal to xi, the distribution on y given x is, well, the number of trials that we have is our x. That takes on the role of n over then y factorial and x minus y factorial. Again, x just substitutes in for that y from that table that we were using. Right? And then p to the y times 1 minus p. Some textbooks will use q here for this whole thing, and that's raised to x minus y. So we have y successes and we have exactly x minus y failures. Right, so reliability in this case of 0.9 of our instrument. Right, so now we start to apply this idea up here, right? That if we want the joint, then we can work with then a marginal and a conditional to get that. And since we have py given x, the form that we want to use in this case is the second one that's up there. So our joint that we were ultimately after here is going to be equal to our py given x, our conditional, times our marginal. Right? And our conditional is our x factorial over y factorial x minus y factorial, p raised to the y, 1 minus p raised to the x minus y. And then we got the marginal here, and that's nu to the x e to the minus nu over x factorial. And notice that in this specific case we have some cancellations here, and we can simplify this somewhat, that our joint is going to be equal to then nu raised to the x e to the minus nu p to the y, 1 minus p raised to the x minus y, all over y factorial and x minus y factorial. And in order to be properly defined, we have to write out what the domain is here. And x is a counting integer from 0 to infinity. And in this specific case, the way we develop this, then y is also from 0, counting integer, but it only goes up to x. That in this particular model, we didn't have any random counts that were not real. Now, if we wanted to have those include that, we could broaden this model to do so.